Hello, and today I am going to teach you about introduction to spectroscopy, which is the first topic in the first unit of AMI. So, spectrometric analysis, which means it refers to the two spectroscopies, actually, which means the molecular spectroscopy and the atomic spectroscopy. In our lab, we are using molecular spectroscopy for the academic purposes, right? And atomic is such a advanced one from this. You can use it to research purpose, right? Spectroscopy means we can understand that we are going to measure a intensity of light which is passed through the sample, right? That is called as IT, intensity of transmittance light. By this way we can conclude the result, right? So we can say that simply spectrometry and spectrometric methods refers to the measurement of intensity of radiation, which is we are giving the radiation which is called as I naught intensity, right? We are giving, and we are going to measure that transmittance light, which means the light is going to pass through the sample, and some of them means some of the photons may be absorbed or scattered or somewhat deflected, anything, right? So after the transmittance we are going to measure that how much amount of light is passed through the sample. So by this way we can easily analyze that how much amount is utilized by the sample. Okay, in between that, photoelectric transducer is needed, because transducers means a device which can convert one form of energy into another form of energy. Here we are going to convert a photonic energy to electronic energy, right? Then the electronic energy will displayed as a digital result, right? So we are giving a electromagnetic radiation which is passed through the sample, but we need a result in digital, so the transducer will do for the do for us. That is important device, electronic device. Okay, actually, and there is a molecule which is called chromophore. If the chromophore is present in the sample, the light will get absorbed, right? So that is the basic principle. Otherwise it may get reflected or it may get diffracted. Okay, the absorbance is due to the chromophore present in that the intensity of absorption is directly proportional to the chromophore present in the sample, which we can say that concentration of the sample. Okay, properties of electromagnetic radiation. There are many properties we have to study in this. Mainly we need wavelength, frequency, velocity and amplitude. Those properties can be studied in a model or with the help of model called classical sinusoidal model. What is the structure we can draw in the board, right? And the amplitude, like that, the normal wave, which is called as sinusoidal wave model. But apart from this, there is another property which is called as particle property, because this light can travel even in the vacuum, right? That is due to the energy particle, discrete particle called photons. So for that we need another model. We cannot study these properties by using sinusoidal model. Okay, done. This, but we can study the particles or photon properties by using quantum physics, right? That is called as discrete particle models. Nice. The most important thing and the principle in the whole spectroscopy, optical spectroscopy, is energy of photon is proportional to the frequency. We should know that because we are going to use variety of energies to study the molecules. If you are giving high energy molecule, it is going to be absorbed and the electrons of the sample can get excited, right? If you give the lowest energy of the molecule, energy of EMR, means it cannot be absorbed, right? Because it doesn't have that much energy to provoke the ground state to excited state. So the lowest energy EMR can rotate the molecule or vibrate the molecule. By studying the vibration, we can easily identify that what is the functional group present in that particular sample. You should be conscious in this. This is the basic principle. I already told you, if frequency is more, energy is more, but wavelength is shorter. If frequency is less, wavelength is lengthier and energy also very less. So it can be started from vacuum to the microwaves or UV to the microwaves, radio waves, like that. Okay, then you see the figure 1 or A, you can see that blue color axis and the arrow headed y axis, in the x axis and y axis. This is actually a plane polarized light. Usually a light particle travels and oscillates in all directions, right? It travels in a straight line, but the oscillation of the molecule present in the light is in all directions. So we cannot use that non-polarized light because the oscillation in all directions, so we cannot get the particular wavelength or get the exact energy. So we should polarize that light. If we polarized, we can use those light for the sample analysis. Okay, and this is recording. This record was I have been recorded in the open air, so you just adjust this birds singing in surrounding. Okay, nice. And picture A, you can see that EMR have two properties. One is electronic property, which is shown by the arrowhead, and the magnetic properties, which is shown by the blue color in the perpendicular, right? So each is perpendicular to each other. Okay, each field is perpendicular to each other. Okay, so in the next picture B, you can see that is the only electronic property of the wave, because we already knew that we need electronic property for our sample, such as we are going to study about the wavelength, frequency, amplitude and velocity, like that. Okay, for that electronic property is more important. So here you should know what is the wavelength and what is meant by amplitude. Wavelength is more important, and that is a distance between two maxima or two minima is called as wavelength. We can denote it as in lambda. That the unit will vary because the wavelength is also vary, right, in the spectrum. So initially the wavelength is very shorter, so when it is go to move to the red end to the microwaves or radio waves end, it is very lengthy. So the wavelength can be measured in nanometer, millimeter, micrometer, millimeter. Sometimes it may be called as a wave number, right? In IR you can see that wave number or micrometer, like that. But when you are using in UV, you should say that in nanometer. That is because it is very initial and high energy source. Okay, and this is all about the wave properties and the electronic fields. So you should see that amplitude also in the previous slide, that is the maximum energy from the source, right? From the 0 to how much it can produce the maximum energy. That point is called as the amplitude of the wave. Okay, coming to this slide, electromagnetic radiation is conveniently represented as electric and magnetic fields. We already knew that. Okay, it oscillates and it is perpendicular to each other of the direction of the propagation also. The term plane polarized, because we should understand this thing, plane polarized means we are restricting the polarization of light in all directions. As a result, we can get in a single directions, because we need plane polarized light for the sample analysis. Okay, all oscillations, the electronic and magnetic field lie in a single plane, which is called as plane polarized. Then electric field strength, this is very basic, right? You just know that is a representation as a vector whose length is proportional to its magnitude. That's all. Then electric component of radiation is responsible for most of the phenomena that are interest to us, including, I already told you, we are more interested in electronic properties of the wave, because by these properties only we can study the wavelength, which is plays an integral part in sample analysis UV spectrophotometer or any other spectrophotometers. Okay, that other electronic properties such as transmission, reflection, refraction, and absorption. Right? Yeah, we already discussed about the what absorption, which means there are chromophores present in the sample which can easily absorb the light and get excited. Okay. Then properties of electromagnetic radiation. You should write nearly 11 properties. You can classify that. The first one is wave characteristics. We knew that one is electronic and one more is magnetic property. Spectrum. Spectrum is nothing but the variety or range of the wavelengths present in the light, right? If we give a single wavelength, that is called as monochromatic light. In the spectrum you can see that variety of frequencies, wavelength, and energy. So that is called a spectrum, that is light spectrum. Right, it is a composition of more wavelengths, that is the meaning. And the third one is magnitude and angular velocity. Magnitude and amplitude are mostly equal, right? We knew that amplitude, that is the magnitude of the waves, how much it can be magnifying with energy in the perspective of energies, right? And the angular velocity, which is most important, the light can pass through in a line, right, in a straight direction, but the particles in the straight direction is moving with the rotational movement, right? How the fluid flow in a pipe, you can understand that. So in such a way it is traveling, so it cannot go like an arrow, right, in a straight line, but it is rotating. Even arrow, if you see in the high tech video camera, you can see that arrow also travel. The high speed arrow is also travel like a snake, right? You can find that if you want, you can search in the net also. You can see that the high efficient videos in that. Okay, those are the physics done. Then superposition means we can superpose the waves which are in the same wavelength or same amplitude, like that. What we can get it from this is we can get the more energy. The superposition are used in laser sometimes. And diffraction, diffract, right? The diffraction means the path length of the light is EMR radiation is slightly deflected from that way, which is called as diffraction. Coherence, co means same, herence means same, presence, right? So coherence, the same as like superposition. The coherence waves are superposed, can be superposed, right? So we can get the multiple energies, we can make the laser, right? Okay, transmission, we already knew that it's going to transmit through the medium. And the refraction, we already know this also, we study in the lower grades, which means Snell's law, sin I by sin R, this refracted. Reflection is the path or the light is nor absorbed or not transmitted, right, by the object or any obstacles, it can reflect it. Okay. Then scattering of the radiation. Scattering is some molecules cannot absorb the light particle, but it can scatter. The scattering is mainly due to the surface of or the shape of the molecules. But there are so many scatterings, Smyth scatterings and Rayleigh scattering, Raman scattering, all those things we will study in the further slides. And the last one is polarization. So we knew that polarization means that is a restricted energy movement in a single direction, right, which is called as polarization, because that polarized light only we can get the exact wavelength or the energy, that finest energy we can get. Okay, in the electrical field, in the picture you can see that those two properties are perpendicular, and we can measure the wavelength by this way. Okay, you can just remember that amplitude, frequency, and period, wavelength, all those things. In this, wavelength is most important, and the frequency you can study in that. But for our aspects, wavelength we are using more than any other words in this. Okay, amplitude means is a length of electronic vector at a maximum in the wave, that is called as amplitude. You can see that in the from the zero it can reach somewhat in the y-axis, right? So that is called as the amplitude. And seconds required for the passage of successive maxima or minima in a space is called period, which means traveling light, right? How much maxima or minima is formed in a seconds, which is called as period. Frequency is the number of oscillations, don't forget, number of maxima or number of minima. Number of maxima and minima are called as frequency, which is the per second. So seconds is the unit time here. And wavelength, you can see that wavelength is a linear distance between any two equivalent points, maybe maxima or maybe the minima or maybe the in between that center point. Okay, is called wavelength. Successive maxima or minima. Okay, done. The multiplication of frequency in cycles per second by the wavelength in meters per cycle gives velocity of the propagation. Here the vector velocity, the unit is meter. So Vi, that means frequency, I means invariant, because the light cannot pass through in the same velocity. It depends on the medium concentration, right? If it is in air, it can pass through much faster than the liquid medium, right? So it's mainly due to the density of the medium. So it is called as Vi equal to V lambda I. The I means invariant of that. Velocity in a vacuum, the velocity of the radiation is independent of wavelength. Understand this and you should note the point. So velocity of the radiation is independent of wavelength in the vacuum, right? You can see in the right hand side picture, see that the lambda equal to 500 nanometer in air, and when comes to the glass, which is such a denser particle than the air, which means the 330 nanometer, right? But in the air also have probably 2, right? And here also have the frequency of 2. So frequency may not change, but the wavelength is changed. Okay, then wave number is defined as the reciprocal of the wavelength in centimeters per centimeter. It is called as wave number. How many number of waves produced per centimeter, which is, and so what is it? It is not working. Oh my god. Okay, it is directly proportional to the frequency. We already knew that. Power is the energy of the beam that reaches the given area per second. How much beam or how much photons reaches to the area per second is called as power. Intensity, which is another more important word we come across for our studies, we should come across, which means intensity is the power per unit solid angle, right? Which is nothing but the concentration of photons which is traveling along with the light rays or magnetic radiation. And see electromagnetic spectrum, see that you can understand this. It is started from the gamma, actually high energy, high frequency but lower wavelength, then X-ray, UV, then visible the infrared, microwaves and radio waves. When it reaches to the radio waves, see that the wavelength is more lengthy, which means lower energy and lower frequency, right? So you can understand this. The color of visible wavelength, violet may absorb at 380 to 450 and blue may absorb at 450 to 495. Such a way you can find this in the slide. Usually the UV spectrum is UV radiation will be in between the 200 to 400 nanometers. Visible is in between 400 to 800 nanometers. That is a rough value. We will see in the next slides what is the exact value which is given in the book I followed, or you are going to follow that. Okay, you can see that how much it is. See that roughly they can say that 400 to 700. Actually 400 to 800 is rough value, and here they are giving that 700 also. Okay, then the concept is type of spectroscopy is gamma ray emission. Wavelength is in Armstrong, right? Gamma is the first one, right? Vacuum, cosmic, then gamma. So this is very first one. So which is in Armstrong, and the type of quantum transition is nuclear. So it can even pass through or change the max as a nuclear. Then X-ray absorption, emission, fluorescence and diffraction spectroscopies are the inner electrons. See that this is also happen in absorption, right? It goes and affect the inner electrons, which means nearby the protons or nucleus, right? And when come to the vacuum UV absorption or ultraviolet visible absorption, what happens? Bonding electrons, you should note that if the energy is higher, it can affect the any electrons which is even nearby the positive energy, which means nucleus, right? But when it comes to the UV and visible, you can see that bonding electrons, which means valency shell electrons. So when we are using UV and absorption spectroscopy, which means 200 to 800 nanometers, it will affect the bonding. So the bonding electron get excited from the ground state to the excited state. We already discussed enough these things in the syllabus introduction, I think. So you should go back and listen that what is meant by phosphorescence and what is meant by fluorescence, and why the phosphorescence is cold light and how much time it is taken. Maybe the gate question which maybe comes, what is the time period of relaxation, or what is the time period of how many seconds it takes for the fluorescence, like that. Okay, IR come to IR. This IR absorption and Raman scattering, and this is low energy molecule when comparatively UV. So it can rotate the molecule or vibrate the molecule. By this vibration we can find that bond length or bond type or what are the elements attached to that, right? So most of the way by using FTIR, Fourier transformed infrared radiation analysis, we can find the functional group of the compound. Okay, then microwave absorption and electron spin resonance, which is more important for us to find out the compound. Still we are using that. That is nuclear magnetic resonance. So spin of the electrons is in a magnetic field is the principle, and here you can see that the wavelength is increasing by nanometer, micrometer, then millimeter. So it is just increasing. So don't forget that if you are using UV visible spectrophotometer, the wavelength will be in nanometer. When you are coming to the IR, it is in micrometer and nanometer, right? Then and microwave absorption is definitely in millimeter. Okay, magnitude and angular velocity. In this you should understand, you can see that right top angle pictures, there are 4 types of waves. You can see that first one is sinusoidal wave model, the second one is I think square wave and the rectangular thing, the fourth one is sawtooth wave. You just listen that, but we are not going to use anywhere in this types. Okay, Okay, in the picture you can see that this is the movement of the electromagnetic radiation. Why pi by 2? Because the movement is due to the angular velocity, angular movement that is rotating. You can see that this circle is vertical to us. You can imagine and think that, right? When it goes, it is a maxima, and when it is rotated again, it is the minima. So that